Let's study 10th standard ICSE Physics, Chapter 9, Household Circuits. Part A is about transmission of power and house wiring, which is not there in the syllabus currently. But we should know the basics of house wiring. So, from the city substation, which you may see in various areas in your city, the electricity is sent to the houses via the wires. There are three wires: the live wire, the neutral wire, and the earthing wire. The live wire can be considered as the wire which brings current to the households. It is connected to a very high potential difference. The neutral wire is connected to 0 volt. So it is simply to complete the circuit so that the current can go back to the source. The earthing wire is just an extra protection. Its importance will be studied soon. Now, just outside your houses or at the ground floor of your building, you will have a company fuse. This is under the control of the company. No unauthorized electrician is allowed to repair it. If this company fuse blows away, then electricity for the entire building or society may stop. Then we have the kilowatt hour meter. Kilowatt hour is a unit of measurement of electrical energy. When you get your electric bill, and if it's mentioned you have consumed 500 units of electrical energy, what is the unit they are measuring it in? Kilowatt hour. It helps us to calculate the monthly bill and pay them. We have a local earthing out there. Then these live neutral earthing wires continue their journey. Live and neutral wires have a main switch on them. This main switch is a dual switch. You can see that when the switch is off, both the live and neutral wire circuits are broken. So electricity can no longer flow into the entire building or the entire flat. Then once it reaches the particular house, we have a parallel arrangement so that we have many electrical power points or sockets throughout the house. Here we may have a fan, an AC, this is for the kitchen, this is for the hall. But each of these has an MCB, a miniature circuit breaker, which is similar to a fuse in that if there is an accidental overload of current, it will switch off the power supply, but only in that area. And remember, MCBs and fuses are always connected in the live wire, not in the neutral wire. And there is a reason behind it, which we'll study soon. Although the main switch, as I would repeat, is connected on both live and neutral wires for extra safety. So even this diagram has to be practiced by all. You can see that if you look at the wiring in the house, inside one house, it is according to the ring system. The live wire carries the current. It has a MCB of 30 ampere. That means if we use a lot of appliances at the same time and together they try to use more than 30 ampere current, they try to draw more than 30 ampere current, automatically the fuse will break and the current supply will stop. Because too much current may not be safe for the wires, they may catch fire. In the ring system, the benefit is that you can always create a new connection from it. You don't have to rebuild the entire circuitry. So here we see one circuit is for the lamp, this is for a socket outlet, this is for the fan. Notice how the fuse is always on the live wire, even the switch is on the live wire. The neutral wire is just for the return journey. Also you notice that even if one of them don't work, the others won't be affected. The circuit won't be broken. Current will still have other paths to reach that equipment. That's the benefit of parallel circuitry. All appliances are connected in parallel, not series in our houses. Now let's move on to the B part. So in the A part, you don't have to do any SEs or exercise. Let's start with the topic fuse. I've already explained what is the purpose of a fuse. It is connected in the live wire to prevent the extra current from damaging the equipments. If there is some kind of an overload and if current more than the required amount flows through it, then the fuse will blow off. So it's a safety device. It puts a limit on the amount of current allowed in the circuit and prevents the appliances from getting damaged. And it works on the heating effect of current. This is the principle behind the working of a fuse. You have to draw this diagram as well. You can see the live wire here. Here the connection is broken. That means current cannot flow because circuit is incomplete. This part of the circuit inside a fuse is made up of a special material of a metal. It's an alloy of lead and tin called fuse metal. Lead and tin alloy is used because its melting point is quite low, 250 degrees Celsius, and the resistance is also more. So if too much current is trying to flow through it, and as current flows through a wire, the wire heats up. That's called the heating effect of current. And the amount of heat can be calculated by the formula I square RT. So if it gets heated too much, this part will melt and the circuit will be broken. The copper wire doesn't melt because its melting point is very high, around more than 1000 degrees Celsius. So it won't melt even if excess current is flowing through it. But that excess current is dangerous for the circuit and for the entire house. That is why copper or aluminum wire is not suitable to be used as a fuse wire. That was a give reason here. Now the amount of current that can flow through the fuse wire depends on its thickness used. For example, for an electrical oven, we know it's going to use around 13.6 ampere of current. So the fuse for this circuit would be 15 amperes. Yeah, it should be slightly more because a little bit fluctuation happens in circuit. We don't want the fuse to blow off again and again. So up to 15 ampere, it can withstand the current. Anything more than that and the fuse will blow. So this will be a thick wire in the fuse. On the other hand, something like a television set, refrigerator, which use less current at a time, they would require a current rating of 5 amperes, which is a standard fuse we can get in the market. This is the lowest value. So that means it will have a very thin fuse wire. So it can melt very easily. As soon as 5 amperes current is breached, the limit is crossed, then the fuse will melt. All these calculations are assuming that the voltage is 220 volt, which is the standard voltage in India. Nowadays we have cartridge type fuses, but the principle is same behind it. Now the question is, an important give reason, why do we connect the fuse only in the live wire? Why not in a neutral wire? Because even if it is a neutral wire, if excess current flows through it, it will melt, circuit will be broken, and no matter where the circuit is broken, the current will stop flowing. That's true. But the problem with connecting it in the neutral wire is that even though current is not flowing, if you notice, the appliance is still in contact with the high potential source. No current is flowing because circuit is not complete, but it is in contact. Now what if somebody is trying to repair the appliance and touches the metal part of it or touches the wire, and the person is in contact with the earth through his feet? So he or she would have completed the circuit now, and then the current will start flowing and the person will get a shock. That is why, to avoid this, we connect it in the live wire. Because if in the live wire the fuse is blown, then the appliance is safe to be used, to be repaired. Even if you touch it, it's okay, because circuit is not complete. Current cannot enter the circuit through the neutral wire, because neutral wire is connected to 0 volt point, where the live wire is connected to the high voltage point. So this was an important give reason. Now how do we calculate the current rating of a fuse? Well, we know this formula, I is equal to P upon V. The same formula to be applied here. MCBs or miniature circuit breakers look somewhat like this. In your house, you may have the main switch for each circuit, for the hall, for the rooms, so that if you switch it off, only that area's connection will be stopped. These are all like MCBs. You may find them near your AC also. They can all automatically trip. So if there is an excess current flowing through it, it trips, it doesn't melt like the old fuses. The benefit is that we don't have to buy a new MCB if it trips. We just have to repair the fault and switch it on again. Whereas in a fuse, if the fuse blows off, you have to buy a new fuse and reconnect it so that the circuit is completed. So MCBs are more convenient and also safer because the MCBs react within 25 milliseconds. The reaction time is very fast, so it's safer than a fuse wire. Next, let's talk about switches. Switch is an on-off device which can open or close a circuit. It is always connected to the live wire. We can have a single pole switch. So if it is switched off, the equipment will stop working because the current will no longer flow through it. A double pole switch can be used at two places. For example, if you have a hall, you can switch on the lights from one end of the hall and then you can switch it off from the other end as well, and vice versa. So we have two switches at two different locations. But the dual control switches are now not in syllabus. But again, why are switches always connected in the live wire? Why not in the neutral wire? Because even if you switch it off in the neutral wire, see here, the circuit is broken. Current won't flow. So what's the problem in connected in neutral wire? Well, the give reason answer is same. Even if it is switched off in the neutral wire, yes, current won't flow, but the equipment is still in contact with the high potential point via the live wire. So if we accidentally touch the live wire, sometimes the plastic coating, the insulation on the wire wears off, and the naked copper wire can come in touch with the equipment, and we might touch it, and we are in contact with the earth, so we are completing the circuit, and then we can get a shock. So that is why the switch should be connected in the live wire, because once that is switched off, then the repairer is sure that while repairing he won't be in trouble. Also, while repairing any equipment, or even while touching any live wire, we should make sure that our hands are not wet, because the normal water, tap water, it is a good conductor of electricity. And even if we don't touch a wire directly, if you're just touching the socket, then the wire, which is deep inside, will come in contact with the water. Water may just flow through this hole, and it can create a connection between you and the wire inside, and you can get a shock. So avoid that. Next, let's talk about earthing or grounding. First of all, we have something called local earthing. So you have to practice this diagram as well. This is the connection to the earth, and it starts at the kilowatt hour meter. If you remember the previous diagram, the first diagram, we saw below the kilowatt hour meter there was an earthing. It is a thick copper wire and a thick copper plate, so that excess current will go into the local earthing. So if there is any short circuiting or excess current overload, then we won't suffer. It would rather go through the local earthing. Otherwise, the line wires are not live wire. Line wire is all three wires combined coming from the substation. But how does earthing protect us? Let's study this with the help of this diagram, which again has to be practiced. Earthing of an appliance. Imagine this is an AC unit. It's a metal case. Live wire enters inside and neutral wire exits. There is a fuse, there is a switch. Perhaps there is a heating element which makes it work. Now what if this live wire accidentally touches this metal case? Usually it is covered with plastic coating or some insulation. But what if it wears off and it comes in contact with the metal case? And then you touch it. So if you touch it with your finger, then the current will flow through the live wire, through the metal case, and through your finger, through your body into the earth. You'll get a shock. The earthing is connected to the metal case, so that if at all current flows through it, the current will immediately flow through the earthing wire into the earth, and that will blow off the fuse. Because here in this circuit there was some resistance inside, so the current was limited. The moment it flows through the metal wire and through the earthing wire, there is no resistance, and the amount of current flowing becomes very high, more than the usual limit, which will blow off the fuse. So the earthing and fuse work in tandem here, and if the fuse blows, we know that something is wrong and we are protected. Even the appliance is protected. Then we just have to repair this, maybe put in new wires and put a new fuse, and we can start using the appliance again. So as you can see here, the wires bring in current here. What if the plastic coating is damaged and it comes in contact with this metal case, or even if there is a metal case inside this plastic, and if you touch it, then the current can pass through your finger and you can get a shock. But there is some earthing connected inside, which is not visible here, and that earthing is connected to the earthing wire of this house, and many such equipments of the house are connected to the same local earthing. So if ever there is any kind of short circuit, then the earthing will protect us. You can see here the earthing is connected to the metal case at this point. So here, of course, the paint on the metal will be scratched off, so that the good connection is made between the earthing wire and the metal case. Next, let's talk about the 3-pin plug. Now in the plug, remember, this left one is the live pin, the neutral pin, and the biggest one is the earthing pin. Whereas in a socket, you will notice in the diagram to the right, you have the live hole, the neutral hole, and the earthing hole is always the biggest one, so that this fits perfectly indirectly into this. They are mirror images. The locations are mirror images, of course. Now deep inside, the live wire is present here, the neutral wire is present deep inside this, and the earthing wire is present deep inside this. The earthing pin is always the biggest compared to these two, because even accidentally we should not be able to put the earthing pin in this or this hole. So to ensure that earthing pin always is inserted in the correct hole, it is made bigger. And it is made longer as well. If you notice, it's longer than the neutral and live pins, so that when you insert it in this, the earthing pin will make the connection with the earthing wire first, and then the live and neutral pins will make their respective connections, so that if there is a fault with the appliance or with the circuit, earthing will protect us instantly. Also note that the pin is split at the ends so that it can fit tightly because of the spring-like action it has. A 3-pin plug is only used for appliances which use heavy current, like the AC, refrigerator, washing machine. For small appliances like mobile charger, they may just have a 2-pin plug because earthing may not be required there, because the amount of current being used is quite less, so the risk is also very less. Also, for the light, all the lights in the houses, there is no earthing wire connection because they are not handheld devices. If you look at this diagram, you will notice that for the socket outlet there was an earthing connection, but for the lamps there was no earthing connection. Even for the fan there is no earthing connection because we don't touch the fan often. Earthing is required for things like AC, refrigerator, washing machine, which are handheld. And now the color coding. You should remember that the live wire's insulation is usually brown, neutral is light blue, and earth is green or yellow. The old convention has to be learnt as well, because some buildings might have the wirings according to the old convention. Also, this helps us to figure out which wire to cut if there is a time bomb attached to you to save you. Only rarely will you find that the person is not wise and he colors all the wires with the same color, so we don't know which is a live wire. Next, high tension wires. Each wire in a cable is capable to withstand only limited current. But as far as electricity transportation are concerned, we need wires which can carry a lot of current. So that's why they're called high tension wire. So the wires are pretty thick. In fact, they might be made up of multiple wires coiled together to give them a very large surface area. Their resistance is also very low, so that there is minimum wastage of electrical energy during transportation. And if there's a large surface area, then whatever heat is produced will be dissipated quickly, so less chances of it catching fire. Next, what are the safety precautions while using the electricity? Well, this is a basic general knowledge. First of all, we know that electric fire is caused because of overheating. If there is a short circuit means the live wire has accidentally come in contact with the neutral wire directly. The insulation has worn out, so there is no resistance left in the circuit. So excessive current will flow, and if there is excess current, there will be excessive heat produced. This can be prevented by using proper insulation, by using a fuse, by using earthing. So all these things should be kept in mind. We should not use wet hands while using appliances. There are 2 solved examples which need to be solved. Otherwise, there are no numericals in the exercise. Here, Roman number 2 is cancelled.
Hi students, this is AJ sir. If you like this video, press the like button. If you would like to enroll for my online test series or online lectures, email me or message me on Instagram. Check the description for more information.